Good evening, everyone, and thank you very much for attending this session, which is the third session of the Siyanqoba Mathematics Training Program for Seniors 2025. Welcome to you. Many of you, you're coming from various places, from Malanga, Fort Hare, and Limpopo, and many other places. So we are going to start now. We'll start straight away with the session problems. I trust that as usual, you had a look at the problems before attending. They were given to you, they were sent to you, either by the South African Maths Foundation or by myself. And as I always say, there is no point in looking at the answer without even looking at the question. Otherwise, it makes no sense at all. All right. Okay. So without much further ado, we'll go straight to my share. Right. Okay. So we are on the right page. Khotso, can you see the first screen?
Yes, I can see it, Prof.
All right. Great. I presume
Okay,
that all will be able to.
before you
Yes.
start, I just wanted to make an announcement. Uh, Hello, guys. Can you please don't leave the class uh, fast today because I'm gonna send the link for Google Sheet where you're gonna fill the form for attendance. The form will be available until Sunday the 3rd, up until from 8 o'clock. Make sure that you have that link to see. We're gonna see it on that registration form that you have attended this session or not.
Okay. Thanks for that notice. Guys, we want to keep a close track as to who is attending. And that is why we need to make sure that you fill in the Google form. Please don't go away without doing so. All right. So the first problem that we have is a counting problem. It says the following. I write down all the consecutive integers from 25 to 208. Kotso, can you read the page? Is it okay?
Write down all consecutive integers from
Okay, you can
21.
read. Okay.
Okay, yes.
Yes, we can read.
Okay, thanks. The other thing is, please switch your microphones off because sometimes we hear strange sounds coming through, the dog barking or the burglar entering the house. So we don't want to do anything, want to have any such disturbance. Please switch your mics off. When the time comes, if it does, then we will ask you to put it on again. Right, so you write down all the consecutive inches from 25 to 2008, inclusive. And you want to know how many digits we write altogether. So we have to count the digits. And the digits are, if you take all the numbers from 25, let's just get this color right. 25, 26, and so on to 208, is it? Yeah. These are the digits, 2 and 5, 2 and 6. So you've written 2 digits here. Altogether, from this point, you've written 4 digits and so on. And you want to know how many digits do you write altogether? Okay, obviously there are 2 types of digits. You've got the 2-digit numbers, which finish at 99. And then the 3-digit numbers, which begin at 100. In this grouping, you count 3 at a time. And in this grouping, you count 2 at a time. So you need to know how many numbers there are altogether. So if you know that, then you can multiply that number by 2, and likewise here. Now, there is a very simple way of counting how many numbers there are in consecutive numbers. A lot of people, if I say how many numbers are there in the sequence, these are consecutive numbers, you might be tempted to say it's 8 minus 6, and you can see that's going to be wrong, because there's actually, that gives you 2 numbers, I mean there are 3. So it's really the last one minus this, but you must add 1 to it. So the number of numbers you've got here, number of digits, equals, how many numbers are there here altogether? It's 99 minus 25 plus 1. Sometimes I like to think of it as the same as minus 25 plus 1 is minus 24. So I look at the number just before this. I don't subtract 25 from 99, I subtract the number before it from. And then you have to multiply that by 2. And then here is 208 minus, now the number just before 100 is 99. So this gives you the total number of 3-digit numbers, but you have to multiply that by 3 to count the digits. So there you have it. You get you got a the calculation can be done, and this I think is 109 327, and you get 477. Okay, so that is the way you do that problem. It's very important to remember the number of ways of counting consecutive digits is the last number minus the one just before the first number. That's the number of, that's for consecutive digits. Okay. Later on, we will come across other counting ones, and we will discuss that when we get to it. Okay, so that takes care of that, and I'm now going to get on to the second problem. Now it says here in the sequence 5, 11, 17, how many terms are smaller than 1000? All right, now we want to know how many. So this sequence here, we should have said this is an arithmetic sequence, and there's a common difference so that we can predict what the next number is. Right? If you're not given this next number, there's no way of knowing what it is, because unless they tell you how these numbers are created. But whatever the case may be, this one is evidently you are adding 6 all the time. So such a sequence is called an arithmetic sequence. And there is a way of counting how many terms there are, right? So you don't know how many terms there are, but in case you, oh no, you are senior students, so you know the formula. The formula is how many terms are listed. The general term, the nth term, there's a formula for this, a plus n minus 1 d. I presume you have seen this before. And a is the first term, n is a number of terms, which we don't know, right? And the common difference is 6. So you've got, when you expand this, you've got 6n minus 6 here, so it's 6n minus 1. So the general term is 6n minus 1. When n equals 1, that's the first term. You will see it's 5. And when n equals 2, that's the second term. It's 12 minus 1, which is 11. There it is. And so on. So this is a formula which tells you what the nth term is, where n could be 1 or 2 or whatever. It's a nice formula to remember, a plus n minus 1d. So you want to know, these are the terms, you want to know for which values of n. So the question is, for which values of n is, this is the nth term, and you want this to be smaller than 1,000. So you want to know which values so that you can count how many there are altogether. So you'll see here that once you got this now, this is the nth term is less than 1,000, then you can actually calculate the n. This is an inequality. So you bring all the n's to one side, as I have done, and then you can divide by 6 because 6 is positive. You can multiply an inequality or divide an inequality like this uh, by the coefficient of n. But if it was negative, then the sign changes. In this case, 6 is positive, so the sign doesn't change. And when you look at this, it's 166 and 5/6. So you want n. Oh, I'm sorry. This is supposed to be n. So the values of n are all the numbers which are less than. So n equals 1, 2, 3, but you cannot exceed 166. It says n is smaller than this number. You're not allowed to put 167 because 167 does not satisfy this inequality. And n is a counting number. So these are the values of n, and it's easy to count them. And the answer is 166. So we've got the values of n, and you can see how many there are very easily. All right, so that takes care of problem 2. The session is being recorded, so if you are, it's always advisable to go to the recording. It's there on YouTube, I think, and you can download that and listen to it and see the whole lesson. In case there are some parts of the lesson which you didn't understand, you can go to the recording and you can control it, slow it down, and go back and go forward so that you fully understand it. Always try to understand everything. Don't leave anything to chance. That's the mantra for a mathematician, a mathematics student. Always ask why and know the reasons why we do things. All right, so now we're gonna get on to problem number 3. Which says the 2-digit integers from 19 to 92 are written consecutively to form an integer. Oh, so you got a huge integer here. Starting from 19, 20, 21, and so on. It's a huge integer. How many digits does it have? Well, you can count the number of digits. Oops. You got 19, 20, 20, 21. So it goes up to 92. So this is just an offside number of digits in this number. Well, it's 92 minus, I'm sorry, 92 minus 18, because that's the number of numbers between. So you see it again now. 92 is a consecutive number. Consecutive numbers. You subtract 18, 1 less than 19, multiply that by 2, and that gives you 148. So this is a very big number. It's got 148 digits in it. But what is the largest value of n such that 3 to the power of n divides this integer? This has got nothing to do with counting the number of digits. So how do we know? So let's understand the question. The question says, find the largest value of n such that 3 to the n divides this integer. So suppose you take any integer, take 36. Right. Now 36 can be factorized. It's 2 squared times 3 squared. Right? And the value of n, the largest value of n, for which 3 to the power of n divides 36. I'm just taking an example. N equals 1, 3 divides 36. N equals 2, yes, because 9 divides 36. But 3 to the power of 3 does not divide 36. So the largest value of n is 2. So to get this, you have to work out the factorization of this huge number, right? And see what's the largest value of n, divides it. If you can factorize it, but that seems to also be a little bit impossible. Okay, so how do you do this? Let's have a look at a smaller figure. Suppose we look at, consider rather, this is too massive. Let's look at, instead of having this huge number, take a number like 19, 20, 21. Let's take that number and see what is the largest value of n that divides this number. Okay, the 3 to the power of n divides this number. Now, the way to do this is to separate the 19, the 20, and the 21. And how do you separate it? This is the same as 19 with 4 zeros. That's 190,000. And then 20 with 2 zeros. I'm sorry, 20 with 2 zeros. And then finally, 21. Add 21 to it. And so when you spread this number out like this, it becomes, see, if you add this 19 with 4 zeros and 20 with 2 zeros and 21, you will see you'll get 21 here, and you got 20, and you got 19. Okay? So we do it like that. Now, now this is 19 times 1,000, 10 to the power of 4. Now there's a trick to this. These kinds of problems always, you know that if you take 1 away from a number which has got zeros behind it, you're going to have a number with only 9s in it. 100 minus 1 is 99. 1,000 minus 1 is 999. So I'm going to take away 1 from this, because I know that if you got all 9s, 9 goes into it, you see. So you've got 19 times 1 with 4 zeros in it. I'm going to subtract 1. And leave the 21 intact. But because now these two are equal, and those two are equal, but I just subtracted 19, so I must add 19 to balance this equation. And here I added 2,000, which is the same as that, but I subtracted 20, so I must add 20 to balance this equation. And you've got plus 21. Now you can see where we are heading. Because if you look at this, it's 19 plus 20 plus 21 plus, now as I said, that's got all nines in it. And this has got 99. So this is 9 times something plus 9 times something, because you got 19 times a multiple of 9, and you got 20 times a multiple of 9. So altogether, you've got this whole thing here is a multiple of 9 plus a multiple of 9. Right? So so in the same way, let me, in other words, you can just add these digits. This number here is equal to 19 plus 20 plus 21. I got an equal sign right throughout, plus a multiple of 9. Okay. So I'm going to do the same thing here, this large number. And the same kind of principle will work, because we are saying if you take any number with one, starting with 1 and with zeros elsewhere, you subtract 1, you're going to get a multiple of 9. So this will work. So I'm just going to remove this page here, and I'm going to say that this number here, let's call it n. N is equal to, it will be 19 plus 20 plus 21, the same argument, all the way up to 92 plus 92 plus a multiple of 9. A multiple of 9, I can say it's 9 times, say, n, where n is an integer. N is a positive integer. It's a big positive integer, but whatever it is a multiple of 9. Because this number here is 99 plus 9999 and so on. So it's a multiple of 9. Okay, now this I can calculate. Right? And this is the sum of, this is an arithmetic sequence. A dot S is an arithmetic sequence. And this is the sum of how many terms? Well, we saw earlier on, this has got 74 terms. It's 92 minus 18. That's, oh, wait a minute. Now, there are formulae for this. There are formulae for the sum of n terms of an arithmetic sequence. And you should know this. I mean, you are senior students. I'm not going to go into the details of this, but it's the two formulae which are quite popular. It's n over 2 into the first term plus the last term. And is another formula is n over 2 into 2a plus n minus 1d. That's coming from, the first term is a, you see. And we saw earlier on we used a plus n minus 1d. So a plus a gives you the 2a. So there are two formulae. If you know the first term and the last term, you can use this formula. Like in this case, we know the first term and the last term. So therefore, we can use the first formula, which says that this is n, which is n over 2 into 2a minus, I'm going to use this formula, n over 2 into t1 plus tn. Now, n we know is the number of terms, and that's 72 minus 18. So it's 74 over 2. And then t1 plus tn is 19. That's your first term. And the last term is 92. All right, so this gives you the expression in brackets there. You still have plus a multiple of 9. Now, here we've got the exact value here, because this is 37 multiplied by 111 plus a multiple of 9. Right? Now, this thing here, 37 times 111, this is 3 times 37. 111 is 3 times 37. So this is 3 multiplied by 37 squared. So the highest power of 3, which divides this, is 3. Right? 9 does not go into this. So, and here 9 goes into this exactly. So when you take out 3 from here, you will have a number which is, take out 3, 37 squared plus 3n. When I remove 3 from this, you can see that this is not a multiple of 3 because it's 37 times 37. This is a multiple of 3. So this whole thing is not a multiple of 3. So the highest power of, the highest value of n, the largest value of n, such that 3 to the n divides this, is 1. That's the highest power. 3 to the 2 doesn't work because this is not a multiple of 3. Okay, so the answer to this question is 1. I'm sorry, I should not have used n here because n is reserved for the exponent. So let's just call this m. That will confuse you a little bit. Let's say 9m. All right, so you have 3m. Okay, so that's the answer to the problem. The answer is small n equals 1. Answer is 1. And this is not a multiple of 3. Okay, so let's just get on to the next problem. We go on to problem number 4. You can see all these problems that we are discussing today are problems on numbers, natural numbers. All right, so the next question is how many 4-digit numbers divisible by 12 can be made using the digits 1, 2, 3, or it's supposed to be 1, 2, 3, 4, and 5. There is an error here. Oh, I always keep making this mistake. Okay, 1, 2, 3, 4, and 5. If a digit may be used only once in each number. So let's understand this question. You want to make a 4-digit number using only these digits, like for instance, 513, right? That's an example of a 4-digit number using only those digits, right? And you can use it only once, so you can't use 2553. That's not in. You can't use any digit twice. All right. Okay. So you want these numbers to be divisible by 12. Now this example here, certainly not divisible by 12. So how do you know whether a number is divisible by 12? All right. Now 12 is actually, if it's divisible by 12, it must be divisible by 4 as well as by 3. So if a number is divisible by 4 and 3, then it must be divisible by 12. So we want to find out which numbers are divisible by 3 and which numbers, and amongst those numbers, which numbers are divisible by 4. So we look at all the numbers which are divisible by 3, and then amongst those, we must try to look at those which are divisible by 4. Now, how do you test to see whether a number is divisible by 4, by 3? I'm sure you know the answer to this. The answer is you'll add the digits. 2 plus 5 is 7, 7 plus 4 is 11, right? Digit sum. Now, this is not a multiple of 3, so this number is not a multiple of 3. It's a simple way of checking to see uh, whether a number is divisible by 3. Now, you're going to leave out one of these 4 digits, right, in creating this digit. If you look at the sum of all the digits, those 5 digits, you get 15. So if you're going to leave out a digit, which digit must you leave out so that the remaining 4 numbers add up to 15? Well, obviously, if you leave out 1, the remaining 4 digits doesn't add up to 15. With a little bit of thought, you will see the only number you can leave out is 3. Because once you leave out 3, you got the sum will now be 12. And that is fine. So the digits, now we know what the digits are. The digits must be 1, 2, 4, and 5. Okay, so now you're going to create 4-digit numbers from these digits here. And I think we've seen these before. So how many 4-digit numbers can you create? It will be 4 factorial, which is 4 times 3 times 2 times 1, which is 24. But that is an aside. Now we want to know a 4-digit number which is divisible by 4. Divisible by 4 now, right? Now, how do you know whether a number is divisible by 4? Like if you take a number like 5, 1, 3, 2, is that number divisible by 4? Yes, it is. The way to check that is you look at only the last 2 digits. If the last 2 digits is divisible by 4, then the entire number is divisible by 4. The reason being that this is 5100 plus 32. See? So 4 is definitely goes into this because this is 51 times 100, and 100 is 4 times 25. So 4 goes exactly into this. So if this is divisible by 4, the whole thing is divisible by 4. All right. So you have to check only the last 2 digits. So you want the last 2 digits to be divisible by 4. So how can you create the last 2 digits? The last 2 digits will have to be, sorry, fine. I want to create a number which is, the last 2 digits is, okay, let's start with 1. You can put 1, 2, okay. That's all. 1, 2, 1, 4, 1, 5. Okay, or you can start with 2, 1. With 2, you can put 2, 4. Okay, that's fine. And then if you start with 4, you can't put anything else here, right? Sorry, that's not what I mean. The last 2 digits. Okay, I think you got the gist of what I'm saying. So I will go straight to that. The last 2 digits have to be either 12 or 24. Those are the only ones. You see? I don't think. Oh, there's also 52. You can have 52. 54 is not a multiple of 4, but 52 is. So the last 2 digits could be 12 or 24. All right, if you take 12, how many digits end in 12? Okay, if you take 12, then you can only use 4 and 5 at the front, but you can put them in either order. Right? So those are two 4-digit numbers which are divisible by 4, right? So you got 2 for 12. Likewise, you got 2 for 24, and likewise for 52, you got 2. So therefore, there are 2 plus 2 plus 2 equals 6 such numbers. Sorry, my writing is very bad. So for this example, this number here is divisible by 12 because it's divisible by 3 and 4. And you can see if you try to divide it by 12, you will see it goes exactly. Just one moment, please. All right, so the idea is you are looking for numbers which are divisible by 3 and 4. Excuse me, still recovering from a cold or a flu or something like that. So you've got altogether there are 6 because there are only 3 numbers which can end in a multiple of 4, and each one allows 2 possibilities. So therefore, there are 6 numbers altogether. Okay, so that's the logic. So let's go on to the next problem. If you have any queries, you can put that in the chat column, and Khotso will alert me to it. Okay, so the next one, I don't put numbers in this, so I don't know what number this is. 8 consecutive positive 3-digit integers have the following property. So you got 8 3-digit numbers, and they're consecutive. Let's just leave the property out for the moment. Let's look at 8 consecutive 3-digit numbers. Right? Now, if you take a 3-digit number, like say 120, 121, consecutive, 122, all the way to 128, now that gives you 9 consecutive numbers, and 129, that gives you 10 consecutive numbers, but you want 8 of them. So you have to either take away the first 2 or the last 2 to get 8 consecutive numbers. Okay. Now, what do they say here? They say each of them is divisible by the last digit. And so if you take, for instance, if you take 122, it's certainly divisible by the last digit, which is 2, because it's even. But this can never be, right? 0 does not go into any number. That's an important fact, right? 0 times any number is 0. So you'll have to eliminate this. So now you've got, it can be, so the last digit can be 1, 2, all the way up to 9. Any one of those 9 digits. But now we don't know whether you're going to eliminate the first one or eliminate the last one. So that is why I've got here now, I've got to make it easy. I put down the last digits are going to be 1, 2, up to 9. And we don't know what the first 2 digits are. And the problem is to find, I just took 12 as a random example. You can see this doesn't work. For instance, 9 does not go exactly into that. Here you say that every one of them is divisible by the last digit. So this one here will have to be divisible by 9. It doesn't work. See? So therefore, these numbers don't work. You can try 121 up to 128, and there you will see, for instance, 127. It is not a multiple of 7. 7 does not go exactly to this. Right. So now you know that every one of them, each of them is divisible by the last digit. Okay, in this case here, 1 always goes into the number, so that's taken care of. This number here, 2 always goes into this because this number is even. That's taken care of. Okay, just hold on with 3. Now here, 5 certainly goes into this because any number ending in 5 will be a multiple of 5, right? Okay, and this you can't say much about the others. All right. So now you want to look. Let's try the first one. Y x3, and that number is divisible by 3. So therefore, you've got y plus x plus 3. 3 goes exactly into this. And the way I write this is up 3 with a vertical stroke, which means 3 is a factor of this number. But you already got 3 here, so therefore 3 is a factor of y plus x. Right. But there's already a 3 here. So 3 must be a factor of y plus x. So in other words, when you add these two, you're going to get a multiple of 3. So what does it mean? Okay, it means y plus x is going to be a multiple of 3. It's going to be either 3 or 6 or 9 or something like that. Right. So we know that as a factor. Okay, so we've taken care of this. Now with 4, as I told you earlier, the x, now the last two digits must be divisible by 4 because you want this number to be divisible by 4. Therefore, x4 must be divisible by 4. And if you put x equals 1, 14, that's not divisible by 4, but x equals 2 works. If you check this thing out, you will see that this thing, x will have to be even. See? If x is 2 or 4 or 6 or 8 or even 0, right? Then the last two digits is divisible by 4. Okay. These x's can be 0. By the way, y cannot be 0 because it's a 3-digit number. So y is greater than 0. So you have to translate the given information into the symbols so that we know, get closer to the solution. Right, so x is even now, and you know that y is greater than 0. So that takes care of this. 5 is taken care of. 6, okay, for a number to be divisible by 6, it's divisible by 2. Well, you can see it's already divisible by 2. And 3. Okay, but we've already taken care of that because then y plus x is a multiple of 3. We know that. So this we've taken care of. Now, this is an interesting one, right? Because you've got this number is going to be divisible by 7. So let's see what we've got here so far. You've got y plus x is 3. So let's see what yx can be. Right, y plus x equals 3 means you've got it. The only way it can be is 1 plus 2. Right? But so you can have 1 plus 2, and but now you put 1 plus 2, 1, 2, 7 doesn't work. Right. So you're going to look at two numbers. You got a 7 at the end, and this whole thing is divisible by 7, which means that this 2-digit number here, the 2-digit number, yx, has to be a multiple of 7. Sorry, my writing is horrible. The 2-digit number is a multiple of 7 because you got a 7 at the end, you see. So you're looking for a 2-digit number. The sum of that is a multiple of 3, and this thing is a multiple of 7. Now, what are the 2-digit numbers which are multiple of 7? So you got 12, the multiple of 7 are 12, I'm sorry. Multiples of 7 two-digit numbers are 14, 21, 28, and so on. 28, 35, 42, and so on. And amongst those now, you want the sum to be a multiple of 3. Okay? So the only thing the only thing it works out is I wouldn't go into the detail, but if you look at the logic of this, it can be either 427 or 847. Right? You want this to be even also. Oh yes, the second digit must be even. So it's 14 or 28. No. Yeah, this 4 must be even. So you get 14, 28, 42. The x must be even, right? And then you get 56, and so on. But then when you put a 7 at the end, then you want, yeah, but you have to eliminate this because the sum of these two is not a multiple of 3. You have to eliminate that. So if you work the whole thing out, you only get 14, 42, and 84, right? Okay, so if yx is 42, then I'm going to take out all these things. I finally came to what yx is. It's going to be either 42 or 84, which brings down the possibilities tremendously. So you're going to have, if yx is 42, then now you try 421, 422, and so on, all the way you come to 427. Now come to 428, that's the next one. You want this to be a multiple of 8. It doesn't work because this is a multiple of 4. 4 times 107 is not a multiple of 8. So this is wrong. This doesn't work. So you can try 841. There's only one possibility now, 843, all the way to 847, 848, and 849, right? And you want, now remember, there are only 8 of these which you need to take. So you either eliminate the first one or the last one, see? But if you eliminate the first one, then you're including the last one, which means 9 goes into this. Now 9 does not go into that. 8 plus 4 plus 9 is 21. And that is not a multiple of 9. You know, for divisibility by 9, you have to add the digits and see whether it's a multiple of 9. That it works only for 3 and 9. Add the digits and see whether it's a multiple of 3. Then the whole thing is a multiple of 3. If it's a multiple of 9, then the whole thing is a multiple. So I can't include 9 because this thing here doesn't work. So the numbers are 841 up to 848. Right. So the question is, what is the sum of the smallest of these 8 integers? The smallest is 841, right? Because we eliminated 849, not 841. And this is the smallest. And the question is, what is the sum of the smallest digits? Always answer the question. Don't stop here. They say, what is the sum of the digits of the smallest of these 8 integers? And then the answer is 13. Okay, so that took a little bit of time because it's quite a detailed problem. Let's get on to the next one. Okay, here you got the sum of 2025 consecutive integers is 2025. What is the largest integer in the sequence? Again, you got consecutive integers, and again, you got the sum of that. And we've seen this before. The only thing we don't know, we know they are consecutive. So the D is equal to 1. And we know the N because you got 2025 of them. So the number of terms there is N. So here you got N is equal to 2025. And A is an unknown, but D is equal to 1. All right, so we need to find A. So the numbers are A, that's the first one. Then it'll be A plus 1, going all the way up to A plus 2024. Because you've got 2025 altogether. So when you count from 1, you come to 2024, but you must include the first one. So the last one is just like A plus N minus 1D. So it's A plus N minus 1 is 2024 D. You can use that as well. Now, we need to add up all these things, right? And the sum, we know the sum is 2025. But we also have a formula for this. Right? The formula for this is n over 2. We know n is 2025. We saw this before. Times the first term plus the last term. The first term is A, and the last term is A plus, this is your T1 plus Tn. In this case, it's n is equal to 2025, because that's the number of terms in this. Okay, so you got 2025 on the left-hand side, you see. So they cancel. 2025 cancel. I can multiply this by 2 on both sides to get rid of the fraction. And you have 2a plus 2024. So therefore, a plus a is 2a. So if you solve for this, cancel the 2's, and you'll have 1 is equal to a. So it's 1 minus 1011. Right? You can do that. It's just one equation, one unknown. And the question again, get back to which is the largest one? The largest of these consecutive numbers will have to be that one, the last one. So the answer is A plus 2024. We worked out A to be minus 1011. And when you add that to 2024, you get 2024 minus 1011. That gives you 1013. So that's the answer to the question. There are lots of little things here, but you will just do it in a systematic way. So we say the sum of 2025, so that means n is equal to 2025. And we know the sum, you know two things about this. And usually if you know two things, you can work out the third one. That's what we've got, because this equation has got 3 unknowns, and d is equal to 1 also. Oh yeah, you need to have 3 things to work out the fourth one. And we have 3 things there. All right, so that takes care of this problem. So the next one we want to do is this one. I hope I haven't left out anything. Sometimes I'm trying to leave out something. Okay, so I'm here now. Now this looks quite frightening. The nth term in a certain sequence is calculated by multiplying together all the numbers like this, some horrible looking thing, where k takes on all the integer values from 2 to n plus 1 inclusive. Now let's try to break down what they are saying there. It's always nice to give an example so you could get a feeling for n. You got n used twice here, so let's give a value for n. Say let n be equal to, don't make it too large, make it equal to n equals 3. Then what happens? All right. The third term in a second sequence is calculated by multiplying all these numbers. So you multiply square root of 1 plus 1 over, and k takes on all the integer values from 2 to 4, because n equals 3. So the k takes on the values 2, 3, and 4. So I must put k equal to, like that, k equals 2. So I'm going to multiply all these numbers like this. Now the first value for k gives you that number. The second value for k gives you that number, 3. And the third value of k gives you that number. And it stops there because k equals 3. So you can only go up to 4. So that, I've given the example. Okay, I didn't realize that was already there. Okay. So now, find the smallest value for n for which the nth term is a perfect square. Now this is the nth term, so we can put T3. T3 is a symbol for the third term. Whenever you're using in a high school, I think you use that symbol. T subscript n is the nth term. So T3 will be the third term. So I just wrote down the third term. But the nth term is the square root of 1 plus half times the square root of 1 plus a third plus the square root of 1 plus a quarter. But you're going to go all the way up to, it goes all the way up to, the last value for k is n plus 1. So it's 1 over 1 plus n plus 1. You see, we put, for 3 we had 4 there. For the n, for n equals, if you don't know what n is, you have to put n plus 1, because the values for k start from 2 and finishes off here. Now let's try to simplify this. These are all being multiplied, so I can have a single square root. Excuse me. So the square root of a product, if you're multiplying 2 square roots, you can make it a single square root. Okay, so now 1 plus half. 1 plus half, look, we've got this 1 plus everywhere. So if you take 1 plus 1 over k, this simplifies. The denominator is k, the numerator is k plus 1, right? It's 1 over 1. So in other words, you get a fraction where the numerator is 1 larger than the denominator. So you know that 1.5 is 3 over 2. So you can see the numerator is 1 more than the denominator. So I don't have to work out all this. I can just put on the denominator is 3, and I'll have 4. Again, the denominator is 4, and the numerator will be 5. It's always 1 more. And likewise, the last one will be n plus 1. The numerator will be n plus 2. Because when you simplify this 1 over k, you get a single fraction where the numerator is 1 more than the denominator. Now, when you look at this, you'll see something interesting happening, because these 3's will cancel, and these 4's will cancel, because the numerator is 1 more, and yet the denominator is 1 more. Is the same. So all these will cancel. The 2 still is alive, by the way. The 5 will also cancel with the next one. And this one here would have canceled with the one just before that. See? So there are only 2 survivors here. That one and that one. All the others, they cancel. So this becomes the square root of n plus 2 over n, over 2. Right. So now they ask the question, so this is your nth term. Right. The nth term of a certain sequence is so on and so forth. Find the smallest value of n for which the nth term is a perfect square. So you want Tn, I just want to create some space here. Let me just create some space so that I can complete this. You want Tn to be a perfect square. So you want square root of n plus 2, that's your Tn, over 2, because the 2 and the n plus 1 cancel, survive. You want the smallest value of n for which this is a perfect square. Now, for this to be a perfect square, this is your square root. This is your nth term. It has to be 1 or 4, that's 2 squared, or 9. But you want the smallest one. So the smallest value of n will have to be square root of n plus 2 over 2 is equal to 1. It's a perfect square. All right, now you're going to solve for n. So you square on both sides, that n plus 2 over 2 is equal to 1. Yeah, and here you see that n is equal to 0, which is impossible. Right. You can't have this term here equal to 1 anyway, because it starts from 3 over 2, not from 1. Anyway, so that is not the smallest value. So now you have to take the next one. And the next one is 4. So you have n plus 2 over 2 is now 4. Because if you make it 1, it doesn't work. You can't have n equal to 0. The number of terms can't be 0. So you got that, and now you square on both sides, and you'll have n plus 2 over 2 is equal to 16. That's how you get rid of the square root sign, square on both sides. And then you get n plus 2 is equal to 32. 16 times 2, and n is equal to 30. So you can solve this equation here by squaring and bringing all the n's to one side. And you see the answer to this is 30. That's the smallest value. All right, so we get on to the next problem. Again, we are carrying on with these sequences. This whole lesson is on sequences. This question says, for each positive integer k, let sk denote the increasing arithmetic sequence of integers whose first term is 1 and whose common difference is k. So you got, it's becoming a little bit more intense here. So you know the first term, your sk is a sequence. Sk is not a number, but it's a sequence. The increasing arithmetic sequence. So we'll just put, normally we put a sequence like that, starting with that. The first term is 1. The common difference is k, so you got 1 plus k. The next one will be 1 plus 2k. Okay, they say that the common difference is k, and that's the sequence that you've got. Right? So for different values of k, you will have different sequences. So if you have k equal to 3, I've got for example, for S3, k equals 3 is 1, and then 1 plus 3 is 4, 1 plus 6 is 7. So that's how you get that one. For k equals 3. So, but you're not told the k. For how many values of k does sk contain the term 2005. All right, so you want the sequence here to contain the sequence, the number 2005. We don't know what position it's holding. All you know is that in some position the number is 2025, right? This year. All right, but you don't know which position. So we'll say it's the nth term, right? We don't know, the position is the n, the first term, second term, the nth term, the position. So Tn is equal to 2025. Right, you want the sequence to contain this number. But we have a formula for Tn. We've already seen it twice. It's A, which is 1, N we don't know, N minus 1, and D is K, a common difference. So that is equal to 2025. Tn is A plus N minus 1D. That's a formula for Tn. So when you substitute that, then we are looking for K, so it's N minus 1 times K is equal to 2024. Because if you bring the 1 to this side. So what does this mean? You got two numbers, which when multiplied gives you this, but unfortunately you got two unknowns here. Now that's the power of working with counting numbers. Because counting numbers, it's not like real numbers. If I say 2, the product of two numbers is 2, there are infinitely many answers for this. I can make x equal to 1/6 and y equal to 6, or whatever you like, you know. You can make x equal to 3/7, and y will be 14/3. And if you multiply these, you'll get 2. So there are infinitely many solutions for that. But here, these are counting numbers. You see, k is a positive integer. So in other words, k is a factor of this. See, k is a factor of this. So k is a factor. Remember, I used the symbol factor like that. So the question now arises, for how many values of k does this thing, the question now reduces to, for how many values, so you want k to be a factor. So the question is, how many factors does 2024 have? So that's the question. Because those will be the values of k. Okay. Now we answered this question. Somewhere, I'm sure I did this, I think in the very first lesson. I said, how many factors does a number have? The way to do that is you factorize your number. I can see 4 goes into this because there's 24 here. There's 4 times 2000 and, oh, I'm sorry, 4 times 506. I can take out the 2 again here. 4 times 2, I got 253. And 253 is not a prime number. It's 8, make it 2 cubed. This is 11 times 23. You have to be a little bit careful here. You have to factorize this into prime factors, right? And the number of factors, 11 to the 1, 23 to the 1. So the number of factors, we have a formula for that. Look, I noticed that George has just entered the waiting room and it's 10 past 6. We started this class at 5 o'clock. People can't just walk in here randomly. It's very unethical. And we'll only allow you to come in for the first 10 minutes. After that, also, maybe we will allow 15 minutes. But after that, we can't allow people to come in here at such a late hour. All right, I have to be a little bit strict on this. Each time you get admitted, there is a noise that comes onto the screen, which is very disturbing. To get back to this, we wanted to know how many factors there are of this this. So the answer is you have to increase each of those exponents by 1. 3 increase by 1, 11 to the 1, 23 to the 1. These are the exponents, and you'll get 16. So there are 16 numbers which contain 2025 as a term in it, in the sequence. 16. And these are the different values of K, see? So, for instance, for example, say K equals 11. We saw that 11 is a factor of this. And then you'll have 11 times n minus 1 equals 2024. So you can work out what n minus 1 is, right? It turns out to be 184. So n is 185. So you got a sequence with just got 185 terms with k equals 11, and one of the terms in that sequence is 2025. So that answers that question completely. I'm not telling you what the sequences are because the question says for how many values of k. So we answer the question, and it's much easier to solve than to write down all the sequences. Okay. All right, so the next problem will be see, people are still entering the waiting room. You can let them in, also, but this is the last time we're allowing people to come such a late hour. Now, this one again, we are working with arithmetic sequences. I can work this thing out, the top one. You've got given that this fraction is equal to 2024 over 2025. Right? What is n? Okay, I can work out the numerator. The numerator is an arithmetic sequence. First term is 1, d is equal to 2, and you know the last term. So I'm going to say the number of terms, yeah, the only thing you don't know is the number of terms here. But it's easy to see the number of terms in the bottom one. 2, 4, 6 up to 2n. So it's 1, if you divide by 2, you get 1, 2, 3 up to n. So there are n terms at the bottom one. And these are in pairs because each one is 1 less than the previous one. So there are n terms at the top. So the top is n over 2. Number of terms is n. First term plus the last term over the bottom is n over 2. First term, which is 2, plus the last term, which is 2n. And that is equal to 2024 over 2025. Okay, so let's just simplify this. You got 1 plus 2n minus 1. 1 minus 1 is 0. So you got n over 2 times 2n. The 2's cancel. And you have n squared. And here, the 2's cancel, and you have n into n plus 1. Okay, so the numerator is n squared, and the bottom one simplifies to n into n plus 1, because this is 2 into 1 plus n, which is the same as n plus 1. So the 2's cancel. And again, the n's cancel here, so you have n over n plus 1. And on the left-hand side, you see you've got a fraction where the numerator is 1 smaller than the denominator. This, when you add 1 to this, so you can see immediately, by inspection, you don't have to calculate this. N is equal to 2024. Because you can see the numerator is 1 smaller than, already you've got this number looking like that. So the answer is looking at you, staring at you in the face. All right, so that's the answer to that problem. You notice I'm going rather briskly because we have many problems to do. and these are being recorded. So if you are finding difficulty catching up, you can always go to the recording and take your own time and study the recording so that you follow what I am saying. Okay, now this problem here is quite a demanding problem. It says, what is the largest power of 2 that divides into this? Okay, so now you got a funny thing. You got all cubes here. 1 cube plus 3 cube plus 5 cube plus and so on. Right. So how do you simplify this thing here? Well, these are very big numbers. And then even if I work every one of them out, 15 cubed is quite a big number. It's 3,375. You're going to add up all these numbers and then factorize it to see the largest power of 2 that divides into that. So, you have to write this thing as 2 to some power multiplied by an odd number. That thing there will be the largest power. It has to be odd here. If it's even, then you can make this larger, you see. The power of 2, you can make it larger because you can bring the 2 out. So I need to write this as 2 to some power times an odd number. But how do I write this? We've never seen this before. So there is a formula here, which is very interesting. And I mentioned this like this. You see, 1 cube plus 2. Let's take the sum of the cubes of the first 5 natural numbers. 1 cube, 2 cube, 3 cube, 4 cube, 5 cube. Right. Now, when you expand this, you will get 225. And then you notice that 225 is 15 squared. But 15 is nothing else but 1 plus 2 plus 3 plus 4 plus 5. That's 15. So it's a remarkable fact for this that the sum of the cubes of the first 5 integers is the sum of the first 5 numbers all squared. It works for everything. Okay, we won't prove it, but if you want to know the proof of that, it's my book. But this it always works out as 1 plus 2 plus 3 all the way up to plus n all squared. Right? Just like this. You simply have to add all the bases and you do, and it's equal to that. But we already know what this is. This is the sum of, this is an arithmetic sequence, and that's n into n plus 1 over 2. So you got n into n plus 1 over 2 all squared. Okay, so that's a useful formula. The sum of the first n cubes is the square of the sum of those n numbers. Right. Now, how does that help us to solve this problem here? Let's call this number x. 1 cubed plus 3 cubed plus 5 cubed all the way up to 15 cubed. Okay. Now, I don't know what this is, but I do know that if I call y equal to 1 cubed plus 2 cubed plus 3 cubed all the way up to plus 15 cubed, I know what this is. But I'm missing the 2 and the 4 and so on. Right? So if I do this, that means I'm adding 2 cubed, I'm adding 4 cubed, I'm adding 6 cubed. Let's not call this y. We can simply say this is equal to, I want to use my formula. I know what this is. But then I've added some things unnecessarily. I've added 2 cubed, I've added all the even cubes. and you're going up to 14 cubed. That wasn't there. These numbers weren't there, right? But I've put them in because I know I got a formula for that. So this thing here is, here n is equal to 15. So it's 15 times 16 over 2. That's what we got here. N into n plus 1 over 2, all squared. Okay. And here you've got 2 cubed, 4 cubed, up to 14 cubed. But these are all even, so I can take out 2 cubed from all of them. 2 cubed, 1. And this is 2 cubed times 2 cubed. I can make this 1 cubed. And this is 2 cubed times 7 cubed. And lo and behold, I got again 1 cubed plus 2 cubed up to 7 cubed. And I know the formula for that. Okay. So what is this? This thing here is equal to 7 times 8. This is 7, n equals 7 over 2 all squared. So I'm going to, because I'm running out of space here, I'm going to just replace only that part, this part here, by 7 times 8 over 2 all squared. Right, so the only problem is that now you got some number now. I got a number. And I need to factorize this and take out the highest power of 2 from this. Right? And without calculators. So what you have to do is 2 goes into 16. So it's 15 times 8. So this is 15 squared times 8 squared. Right? And this is minus. Here you got 8 times, you got 2 times 4. 2 goes into 8 4 times. So this is 7 times 4 is 28. So this is 28 squared. I'm going to make it 4 squared times 7 squared. Right. So I can take out 8 squared from this because this is 16. This is 2 times 8 here. So I can take out 8 times 8 from this, 8 squared, and the remaining factor is 15 squared minus, when I take out 8 squared from this, I got 8 times 2 times 8 times 7 squared. Take out 8 squared, you get 2 times 7 squared. Okay? And when you work this thing out here, this is 225 minus 90. This is an even number here, and this is odd. So you have odd minus even will be odd. So you got this is 8 squared times odd. 8 squared is 2 to the power of 6 times an odd number. 8 is 2 cubed. So 8 squared is 2 to the power of 6 times an odd. This thing here is odd. Why? Because it's odd. 15 times 15 is odd. And this is even. Odd minus even. Don't even have to calculate it. Odd minus even must be odd. Okay? So the answer is, we've got it in that form. So the answer is 6. That is the largest power of 2. The largest power of 2, which is a factor of x. Okay. So that takes care of that. Now I'm running out of time. I've only got 3 minutes left. Let me just see what problems I've got here. What's left? Okay, I'll finish with this. Okay, we can leave that out. Okay, let me just do this last 2. I'm going to leave one of them out, and you can check. I think I'll record that and post it, but we can't do that now. I may record it. Those who want to go away can go. But let me just do these last two first. 25 points are placed inside a 6 by 4 rectangle as shown. Prove that there exists at least two of the 25 points that are separated by a distance d, where d is at most 2, the square root of 2. Now this looks really weird, but I'm just going to explain here what the logic is. You see 6 by 4, I can divide it up into a grid like this, right? Where I got 4 rows and 6 columns, right? It's 6 by 4. And now I got 24 squares, right? Now you got 25 points are placed into 24 squares. There is a conclusion from this, right? If 25 points are placed into 24 squares, you can't have only one in each one of them. That'll only give you 24 points. So the worst case, you can have 24, only one, each one of them. But you will always have at least one of them will have two points. Because you got more points than squares. So one of them will contain at least two of them. It's a simple logic, but there is a thing called the pigeonhole principle. If you want to know more about this, you can read this. Read pigeonhole principle, and if you got my book, you can read there as well. So what it says is that if you got n points and only got m pigeonholes, and you got n pigeons, and you got more pigeons than holes, then some pigeon will have to occupy, two pigeons will have to occupy at least one hole. So there are two of these points must be in one of those squares. So when you do that, then you see that what happens is that, oh God, sorry. So if you look at that square, you got 2 points inside there. And all these squares are 1 by 1 because we broke it up into 4 by 6. These are 1 by 1, and there are 2 points inside here in one of these squares. We enlarged it, right? And they say, prove that there exists at least 2 points. I've got 2 points that are separated by a distance d. The distance between these points, this largest distance it can possibly have, is the diagonal. This is the longest distance between 2 points inside the square. And by Pythagoras, if the sides are 1 and 1, this diagonal is square root of 2, right? Pythagoras' theorem. So the largest distance between these 2 points is square root of 2. You can have the points in the corners, and so this distance here between the 2 points is always smaller than that, right? It could be, is at most, so the distance is less than or equal to square root of 2 if the points actually are in the corners, right? So that takes care of that problem. It's called it's an application of the pigeonhole principle, and you can go and read up on that because it's a very interesting principle which can be used to solve a lot of interesting problems. And it's so simple. It simply says that you must have, if you got more pigeonholes than pigeons. This is regarding, when they send pigeons to do, they used to use them as carriers. So that is why it's called that. Okay, to get back to this one here, the last one is this. You got this funny looking number here. Find the exact value of this without using a calculator. Right? And this is a good example of how you can use the power of algebra to solve this, right? And it's quite unusual because normally you let x be an unknown, but here you let x be a known. And then if you let x be a known, namely, you can see you got all fours here, and this is 2 times all fours. So let x be equal to 444,444. Then I'm going to try to simplify this number here. Let's call it n. So what is n then? Now, I'm going to try to write this entirely in terms of x. Now here I've got 4. This number here is, I can put 444, 444. Let's go to that. And I got 6 zeros. And then plus 444, 444, right? We're adding. So these two add up to the first number, but you got minus 2 times 444, 444. So now you can put, we know that this is x. So we can write this as x in terms of x. What do you have? You have that this is 10 to the power of 6, a million, times that number, which is x, right? Plus, and this is x minus 2x. You see how this monster is tamed. I call this taming the monster. Right? You can get everything in terms of x. And then you got this is square root of, now x minus 2x, this is minus x. So you got 10 to the 6th x. So if you take out x as a common factor, x times 10 to the 6th, and this is minus x, so it's minus 1. If you expand this, you get x times 10 to the 6th minus x. Right? And that gives you square root of. Now I can I'll put back my x here. But now this is a multiplication, you see? It's not a subtraction anymore. You converted the subtraction to a multiplication. And that's by factorizing. That's the power of factorization. It converts multiplication to factorization. So you got, this is 444, 444. And you're multiplying this by, earlier on I told you, you got one with several zeros, and you take out 1 from there, you're going to have only 9s. All right? And now this gives you, got the square root of that, but you see a number being repeated here. This is 111 squared. Oh, 111. Okay, so this is actually 36. 4 times 9 is 36. Square root of 36. And if you take out the 4 here, you get 111, 111. If you take out this 9 from here, you get 111, the same number. So this is 111, 111, all squared. So you got square root of 6 squared times 11 squared, and that is equal to 6 times 111 squared. And that, you don't even need a calculator for that. 6 times a number with all ones and is 6. A number 666,666. It's a beautiful application of algebra where without a calculator you can work out something like this by just using a symbol for a rather clumsy number. I often do that whenever I have something clumsy, I'll put a symbol, a single symbol, and then work with that symbol right throughout. And at the end, I bring back that symbol, and you will see that a lot of problems can be solved like that. So this is a good example of using a symbol for a complicated thing. Well, thank you very much for those of you who have remained behind, for staying here. We have come to the end of this, but I can work out this other one. Those who wish to go can go, but I'm going to quickly work out the one that I missed out so that this lesson will be complete. Okay, I left that one out because it looks a little bit complicated. So here, so determine the sequence that has the smallest value. So I'm going to go through this thing quickly. So you got a sequence here. The first term is those two. There's a comma here. Those two are added. Those two are added. So there are 4 terms in the sequence, right? So let me just see what the nth term is. The first term starts with 7. The next term starts with 8, 9. So here you got n plus 6 because you got a n equals 1 gives you 7 there, but the denominator is 6. The denominator is 6 for this first term plus the square root of 96. The 96 is all over the place, so we can put 96 here, but the denominator here runs from 7, 8, 9, etc. So that is also n plus 6, right? So now this is your nth term, and you want to say what is the smallest value? What is the smallest value of this? There are several. You can put various values of n here, and which is the smallest value? Okay, so the trick here is you take square root of n plus 6 over 6 here, but this one here is 6 times 16, you see? 6 times 16. So it's 16, you can take that 16 out and make it square root of 16 is 4, and then you have 6 over n plus 6, right? When you take the 16 out. But then you see that this number here is exactly the same as this, but it's reversed, right? So this is a, see, again, you let a be equal to square root of n plus 6 over 6. This is what I said earlier on. You take something nasty, you see it's repeated here, so you can make this 4, and this is 1 over a. This is the reverse of this, the inverse of this. So this is 4 over a. So if you put 1 over a, you get square root, you get precisely this. So now you need to work out the smallest value of this. Now we are not at the end of the problem. You see this a here. And there's a trick here. This is the square root of a all squared, and this is 2 over square root of a all squared. The square root of a all squared is a, and 2 over square root of a all squared is 4 over a. So now you got 2 squares here, right? And if you got x squared plus y squared, right, you can add or subtract 2xy to this, and you will get a perfect square, right? And that's what I'm going to do. This is square root of a, but I'm going to make it minus 2 over square root of a all squared, right? The reason for that is then I will see that the first term and the last term of this is that. This is exactly the same as that, except that the middle term is the product of these two, and I've added, it's got a minus the product of these two inside here. So I have to add. This is a well-known trick. If you do a lot of Olympiad problems, you will know that this is how you have to do it. So you got minus 2 times this product here has been included in this, and we're not supposed to have that. So therefore, I have to add that same thing to make this balance. Why do I do this? Because this is a square, you see. So this is always greater or equal to 0. So therefore, this whole number here, this part here, square root of a cancels, and this is equal to plus 4. So this number here is always greater or equal to 0 plus 4. Right? So 4 is the minimum value. They say determine the term in the sequence which has got the smallest value. So the smallest value occurs when this part here is 0. Because the smallest value of this is 0. So the smallest value occurs when this is 0. Let me just... This is quite a tricky problem, but I'm sure when you go over this thing again, you will understand what I am saying. So let me just write this down. So the smallest value of is 4, right? This is coming from here. And this is obtained when this part here is 0. Right. Now you can solve for a. Because you got root a equals 2 over root a, multiply, and you got a equals 2. Right. So the smallest value occurs when a equals 2. But if you remember, we said a was actually, we gave a name. We named something as a, and that something that we named as a was square root of n plus 6, I think. Oh, it's here. Oh, good. I didn't rub it out. Okay, so then you got this is equal to 2. So you have 2 equals square root of n plus 6 over 6. So that allows you to solve for n. So you can square on both sides, n plus 6 over 6 gets rid of the square root, and then you get n plus 6. Multiply by 6, you get 24. 4 times 6 is 24. And solve for n, you get n equals 18. So this is a tricky problem, but you have to make some adjustments as you go along. And in the end, you have to rename and observe something that you can make it a square using the fact that a square is positive or it's non-negative. All right, thank you very much. I've gone beyond the time. Let me just see if there's anybody who's asked a question. Sorry, Khotso, I went beyond my time as usual. Oh, there are still 15 people here.
No problem, Prof.
Okay, thanks, Khotso. There are still 15 people, which is quite nice. And remain behind, Khotso. I just want to ask you something. So there are no questions. This is all right. This is just an admin statement. Okay. If amongst you who are present here, is there anything that you need to ask me? Feel free. I want to thank you for remaining yet till the end. As you can see, each one takes a fair amount of time. Okay, are there any questions?